All right, welcome to the second part of section 1.3. We're still talking about continuity, and now we're going to talk about two new things, or actually one new thing. We've already talked about limits and continuity. Now we're going to talk about this idea of end behavior. Okay, so we're still, the essential question is what types of graph specific characteristics are important for functions. We're still talking about that, and then the one we're going to talk about today, the new one is called end behavior. Okay, so what we're going to learn. We're going to learn how to use the intermediate value theorem to show zeros of a function. Okay, so this intermediate value theorem, it's actually pretty easy to think of. And we're going to use how to use limits to show end behavior of functions. And this is also a pretty easy topic. Neither of these are very challenging, so this should be a good video. All right, so the first topic is, what is the intermediate value theorem? Okay, and we have this very complicated chart here, but really it's not that difficult once you just kind of have to know what's going on here. Okay, so let's say you plug in some x value a and your answer is down here, so it's a negative answer. Okay, then you plug in some b value and you get a value up here which is positive. What this is saying is that if you plug in A and it's negative, and then you plug in B and it's positive, there has to be some zero in between there. It has to cross the x-axis. If you get a negative for one number and then you get a positive for another one, there has to be a zero in between there. Okay, so that's all that's saying is. So what's saying is this. So, all right, sorry, I had to get rid of my annoying cat. So what it's saying is if you plug in A and you plug in B, so here's A, here's B, there has to be some zero in between there if A was a negative value and B was a positive, or vice versa. If A was positive and B was negative, there has to be a zero in between there. So that's all that's saying. All right, so let's look at an example. It says, determine between which consecutive integers the real zeros of each function are located on the given interval. Okay, so what we have here is this. We have a function f of x equals x cubed minus 4x plus 2, which you could graph on a calculator, and it wants us to show where the zeros are between negative 4 and 4. So what I've done here is I've made a table. Okay, and you can create your own table. This is very easy. So if we plug negative 4 in for x, we get negative 46. Negative 3 is negative 13, negative 2 is 2. So, all right, so here's my x values from negative 4 to 4, because that's what it wants us to do. And we can see our signs of our functions. So negative, negative, positive. So what this is saying is that since negative 3 was a negative answer and negative 2 is a positive answer, there must be a zero between negative 3 and negative 2. Okay, so that's what that's saying. So let's keep going down the list now. Positive, 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 positive. Now, once again, right here, it goes from if I plug in 0, I get positive 2, and if I plug in 1, I get negative 1. There must be a 0 in between there because it changes from positive to negative. And if we notice again now, it's negative at negative 1, and then it's going to go to a positive. So between here and here, there must also be some 0. So between 1 and 2 must be a 0, and between 0 and 1 there must be a 0. And then it just stays positive for the rest. So anywhere that it switches from negative 13 to 2, and 2 to negative 1, and negative 1 to 2, there has to be a 0 between those integers. So there's going to be a 0 between negative 3 and negative 2, between 0 and 1, and between 1 and 2. So let's check the graph. So if all you do is graph this on the calculator, we can see. Let's see, between negative 3 and 2. Okay, here's negative 3, and here is negative 2. Is there a 0 between there? Yep, it's right here. Okay, so it's really close to negative 2, but it is in between negative 3 and 2. All right, now let's check between 0 and 1. Here's 0, here's 1. Is there a 0 between there? Yep, it's right here. Okay, and now between 1 and 2. Well, here's 1 again, and here's 2. Is there a 0 between there? Yep, crosses right there. So there is a 0 between anywhere it changes from positive to negative or negative to positive, vice versa. All right, let's look at the next one. Now, a lot of the work is done for us here, but you could make your own chart very easily. All right, so here's our new function, x squared plus x plus 0.16, and it wants us to check between the interval negative 3 and 3. So I made a table, If I plug in -3, I get 6.16. If I plug in -2, I get 2.16. If I plug in -1, I get 0.16. So let's see where it changes from negative to positive. And if we notice, everything is positive here. There is no change, okay? But we can see, though, we can make a little inference here that it's getting smaller. So going from here to here, it is decreasing. And from here to here, starting here, it is going increasing. So just because it doesn't change from negative to positive or positive to negative doesn't mean there isn't a zero. It just says there will be a zero if it does do that. But however, if we notice here, it's decreasing, it goes to 0.16, 0.16, and then it goes right back up, 2.166. So if I look at the graph, we can see that it doesn't necessarily cross, but it can come down here and touch. So there's probably a zero somewhere in between these two spots. Somewhere in here, there's got to be a zero. Okay, so if you see a pattern where it's decreasing and then it's increasing again, there's probably going to be a zero again. But in the last one, if it switches from negative to positive or positive to negative, there has to be a zero there. Okay, that's all this intermediate value theorem is saying. All right, so that's part one. Part two, okay, so here's part two of this particular video, is what is end behavior of a graph? And it's as simple as this. The end behavior of a function describes how a function behaves at each end of the graph. So the right side and the left side. And what this means is as x increases and x decreases. All right, so we're going to write this like this. What is the limit as x approaches positive infinity? Okay, so what does that mean? That means as our x values are going towards positive infinity, what is the graph doing? Okay, so we want to know what our function is doing. So if we notice, where's our function going? It's going as x gets bigger. So as x, here's 1, 1, here's 2, it's going here, 3, this graph is up here. It is going towards positive infinity. It's going straight up, and it's going on forever. So as our x approaches infinity, our y is also approaching infinity. Okay. Now, what happens if we do it the opposite way? What happens if x is approaching negative infinity? So what does that mean? That means our x's are going this way. What is our graph doing when our function is getting more and more negative? So what's our function doing now? So if we notice, our function is pointing straight down to negative infinity. So as x gets smaller, y is also getting smaller. So as x gets smaller, y is also it's going down. On the right, as x was getting bigger, our graph was also getting bigger. So it was going towards positive infinity. The left side is going towards negative infinity. All right. So let's do a couple examples on this. All right, so it says use the graph of the following function to describe its end behavior. So we have this big function here. I had to change my window, but this is what I got. All right, so we have two answers here. We want to know what x is doing as it approaches positive infinity, and we want to know what the graph is doing when we approach negative infinity. So we always finish it with f of x. All right, so as x gets bigger, what's our graph doing? It's pointing down, so x is getting smaller. So it's going towards negative infinity. Okay? Now what happens if we go the other direction? What happens when x is getting smaller? What's our graph doing? It's also going down. So both of these answers are going to be negative infinity, which is okay. If they're both pointing up, then they'd both be positive. But both of these are finishing going straight down off the screen. So they're both negative infinity answers. Okay, so this would be your answer for the positive infinity version to the right hand side, and this is your answer for the left hand side. All right, let's look at example 4. It says use the graph of the following function to describe its end behavior again. All right, so here's the function. They may not necessarily give you the graph in the homework. You might need to graph it on your own, but here is what the graph looks like. So let's do the right hand side. The limit as x approaches positive infinity. So we're going to the right now. What's the graph doing when we go to the right? Well, it's going straight up off the screen. So your function is equal to positive infinity because it's going straight up off the ground. So here's our right-hand side answer. And now let's do the left. The limit as x approaches negative infinity. What is your function doing? All right, so when my x gets smaller, what is my function doing? It's going down and off the screen. So this one is going to approach negative infinity. Now, it's not always this easy. Okay, it's not always just going to be positive infinity or negative infinity. What happens if we have an example that looks like this? It says use the graph of the following function to describe its end behavior. Okay, so I have a function, I graphed it, and this is what it looks like. So notice that it's not just going up and off the screen or down and off the screen on either side. It's actually going down and it's getting closer and closer to 0 on the right, and it's doing the same thing. So this is called a horizontal asymptote. We've talked about that before in Algebra 2, but both the right-hand side and the left-hand side are approaching the same number. So this is how we write it. The limit as x approaches infinity, f of x is equal to, where is it getting closer and closer to? It's getting closer and closer. And if I extended the screen, you could see that it's getting closer and closer and closer to 0. So the answer would be 0 for the right. And let's see what the left side is doing. So what is it doing when it's approaching negative infinity? And if you notice, it's doing the same thing over here. It's getting closer and closer and closer to 0. Now, how could I be sure that that's the answer? Okay, I'm going to go to my calculator. I'm going to plug this equation in. X divided by, and if you're dividing by a polynomial, you're going to put it in parentheses. So x squared minus 2x plus 8. All right, and I'm going to graph it. There's my graph. And what I want to do is I want to look at the table. So I'm going to change my table. I want to start my table at 0, and I want to go by hundreds. Okay, because I want to see what it's doing when my x's get really, really big and really, really small. So I'm going to go to my table, and let's see here. So here, starting at 0, let's see what happens when my x's are getting bigger and bigger and bigger and bigger. So notice 0.011, 0.0102, 0.00505, 0.00336, 0.001. Notice it's getting closer and closer and closer to 0. 9.1 e to the negative fourth, that means 9.1. And that's 4 decimals to the left, so that's 0.000091. The next one's 0.000083. So these are getting really, really small. And if we go the other way, the other direction, notice that they're just getting closer and closer and closer to 0. Same thing. They're getting really, really small. All right? So that is why we can tell that it's getting really, really close to 0. Okay? So that's end behavior. How does the graph function look on the right-hand side and the left-hand side? And then how can we determine if a function has zeros based on this intermediate value theorem? If a number is negative and then it turns positive, there's got to be a 0 in between there. Okay? So we'll talk about this more tomorrow. Have a good night. I will see you again later.